Oh, you mean like now? That's Saturday. Yeah, I don't want to something to run early. Yeah. So you get that with some time, but not enough time to do it. Yeah. Oh, it depends. I don't know what the stats of this. Of the 3 remaining games, it's the one that we're least at. And it's also the game that matters the least because they're not aces. I think we have a pretty good chance of against Miami because their quarterback likes to throw a lot of interceptions. I think we check that Mahomes sits on their turf. Let me remind you of something. Yeah. Georgia Tech is pretty good. Georgia Tech is pretty good. I don't know, we're never going to have to know. And they're one in the ACC because we haven't lost their it's not, so the reason it's 4 and not 5 is the first year you just added. Do you know which game was funny? And I watched it live. Oh, like on the 4th, that was I like it better in some ways than NFL because because then you get tied in. But this was very fun. What do you mean frustrated? This is good. In terms of like team in terms of football, I'd say that he's there. The players are nice. That's fair.
Yeah, you should get like 3 million. Not because you have to go down. Yeah, that's right. You use that, you have to, and then you have to do the.
That's because
So then you have to get that subtract 705. Once you like, it just cuts this out because I hate doing this. It's really not that hard. You know how to get that number, that's easy. Doing that, I mean, but like, it's not showing you how to get that because there's another thing you do to get that. Right.
Georgia Tech they're going to win against Washington. Virginia, they're going to win against Virginia. They're going to lose against the what?
All right, happy Tuesday. How's everyone doing? Isn't it lovely outside? I mean, Yeah, the snow's nice.
For now.
It's better than rain, for sure. All right, well, I was visiting family this weekend. This is a picture of 4 generations. I think this is amazing. Maxine, mom, grandma, great-grandma. What a delight. So we have a medium-sized one today. We are wrapping up part 4.3, categorical variables, categorical predictor variables, with a bit of an exercise. So we're going to do an exercise at the beginning here. Then we're going to jump into time series, which I know is everyone's favorite topic. We're going to talk about a couple of problems that we have to deal with when we talk about time series models. And then I'm going to strongly discourage you from working on time series for your final project. And then we're going to do a bit of an exercise with time series data as we go through that. This should take us hopefully less than an hour. What I want to do at the end of class is give you a bit of time just to check in with each other. And then if you want to chat with me about your final projects, this is a good chance to do that. I'm scheduling a review session for the mini exam tomorrow afternoon. If I did this, how many of you would be interested and available to come? Like maybe 4 o'clock? No guarantees. Hands high? Okay. A bit of interest. So we'll see what I can do. I'm definitely recording and posting the mini exam demo, which would be very similar to what we would do in the review session. So we'll see about the review session. And then mini exam on Thursday. So this will be our first Thursday mini exam, just to give us a bit of extra time. The last one will be the end of the first week of December. So we come back from Thanksgiving, and then our mini exam 5 will be during that week, right before finals week. Let's see. We have the 2 homework from last. Do you say homeworks? I do. Yeah, I think the plural of homework is homeworks, right? Okay. So I'm not strange for using that. My wife makes fun of me sometimes for it. Okay. Yeah, so that's correct. Homeworks. 2 last week. There's going to be 1 this week. So no time series homework and no causality homework. So just homework 4.3, which we are going to do in class. Y'all ready for that? So we're going to talk about categorical predictors and then talk about time series. And we're going to start with a bit of a refresh. But you all doing okay? I'll take that as a medium. If things are falling through the cracks for you, I love it when you reach out. Just let me know that you're like where you are and how things are going for you. I appreciate it when people do that. We can even sit down and have a chat. Those things I think are really nice. Just let me know how things are going. All right, so last time we talked about categorical predictors. This was essentially just the extension of the general linear model to cases where X is a binary categorical predictor. So this was the general idea when we have one predictor variable. And it turns out this is super flexible. That's like the big point of parts 3, 4, and 5. The general linear model is incredibly flexible. So the idea with the intercept-only model is that it was a univariate one sample t-test. So we're just checking where the mean is, essentially, which is a intercept-only GLM, which looked like this. This was the numerical predictor model where we had some running variable on the horizontal axis, and we were just trying to find a relationship between x and y. So some relationship between the x variable and the y variable. And we built a model that looked like this. So this was, the data points, the model running through the data points, and then the error, how off the model is for each one of these values. And then we try to minimize the error, and that gives us a nice little model with some coefficients, like our mx plus b terms. So we have m and b, and that allows us to make interpretations about the relationship between the variables. And the important thing is, because we don't know the underlying distribution of the data, we can make claims about how confident we are the beta terms are different from 0. This was with the sampling distribution. Last time, we introduced this kind of question, where we said, on the horizontal axis, instead of having numerical variables run from like whatever they are, here we're going to force them to be either 0 or 1. Sometimes this is what our data looks like, we can just plot our data in exactly the same way. Someone after class asked about, what's the horizontal dimension here? I forgot to mention, this is just the horizontal jitter, just to make the box plot look nice. All of these values are at 0 on the horizontal axis, and all of these values are at 1. I think we might have done a little bit of this in the exercise, but this was the basic idea. We can organize our data as a binary predictor variable at 0 and 1. And then our statistical model is just checking what happens as we move along the horizontal axis, which in this case means we go from 0 to 1. So it's the same interpretation with a horizontal variable being continuous numerical. In this case, the interpretation is exactly the same. So beta 1 was just the slope of this line. So we fit our model to the data. We get a vertical intercept at 0, which gives us the average temperature of the 0 group. So that's our beta 0. And then we have the slope, which tells us as we move from 0 to 1, how different is average temperature. So on the vertical axis, how different is the temperature. So we go from 0 to 1, that's our x variable, and our beta 1 simply tells us how different the second group is. So here the beta 1 tells us the difference in the averages between the two groups. Because we have two groups, binary categorical predictor variable, and this tells us the difference. In this case, this is pretty nice. It tells us that the average temperature in green space, high green space neighborhoods is like 2.6 degrees lower Celsius. How many of you think in Celsius? Nice. Respect. I wish I did. Unfortunately, I think in Fahrenheit, which is empirically the worst measure. I just can't get my brain to think in Celsius for some reason. But yeah, so this is in Celsius, which is 2.6 degrees is a lot in Celsius. So it's telling us the difference in means between the two groups. Okay, so this is really nice. And then our p-value is just essentially the probability of drawing a slope like we have in red from the null distribution of no slope, which is a bunch of these gray lines. So how likely does this look like it's coming from these gray lines? Well, very unlikely. They do not look the same. So we can, in this case, at some level of confidence, we say we reject the null hypothesis. We're very confident that the null hypothesis of no relationship between green space and average temperature, we say it's very unlikely that there is no relationship. Okay, any questions here? So this is nice. Did we walk through some of this? I can't remember if we got to this exercise. I think we I threatened to start, and then we ended early because I wanted you to have some extra time to chat. So this is an exercise. It's posted on the course page, so you can take a look at it. So this is under part 4.3, categorical predictors. So if you click on this, it'll open the exercise up for you. And then in the slides, I've given you, how nice of me, I've given you all the steps and all the little bits of code. So you can walk through this. I recommend doing this, but I think for the sake of time, we're not going to do this exercise. Instead, y'all want to do some homework together? Nice. So what we're going to do is do homework 3.4. And we're going to treat this like almost like a study session. We're going to do this a bit sort of together, but then also I want you to be checking with each other about your results. So just a little extra bonus right before the mini exam for being good citizens. Okay, so homework 3.4, here's the assignment. It's not posted on Gradescope yet, so apologies. We're going to work with a data set that you're familiar with. I think this was in homework 4.1 that had the mental health data set. So this is just a data set on behavioral risk factors, just a surveillance we do taking surveys of the population just to try to understand risk factors at the individual level. And what we have here are, so you can load the data in this notebook. I guess I didn't provide you a direct link to the data set. But if you run this and load the data set, you should see a couple of variables here. The individual, we have this income to variable, which is a little different than you'd expect from an income variable. So we'll talk about this in a second. And then you have this mental health variable. These are also, we have some geographic data here. So this tells us the county and the state. We have the unemployment rate, the year it was collected, and then some other information that we're in the homework. I haven't given you a lot of information about, but this is like a college binary predictor variable, whether you're married, whether you're female. And then we used this BMI indicator, continuous numerical variable, for one of the, it was either 4.1 or 4.2 in the homework. Okay, so nice. We have all this data on all these individuals. We can see how long this data set is. So there are, let's see, 243,000 observations in our data set. So this is not small. There's a lot going on here. So in the homework assignment, we have a bit of information about how income 2 is coded. So if you look at income 2, you can see that it goes from 1 to up to 8, and then it jumps. We have 77, and then we have 99, and then we have blank. And the first question, so this just represents a bunch of different categories here. So this is different income groups up to 75,000 or more. Then we have these two weirder looking ones. And these numbers, we often use these kinds of codes as a way of communicating some extra information in a variable like this. 77 is when someone reports that they don't know or they're not sure what their income is. 99 is that they refuse to tell the survey collector how much they make. So this is refused. And then if it's blank, then we say that it wasn't asked or it was missing. So this is just a way of sort of thinking about the variable. When we get started, whenever we work with variables, you're going to encounter this in your final project. You're going to have to think about which variables are doing what and what the numbers or the categories in your variable represent. So in this case, we actually have to be pretty careful about this. So this is a great question to start thinking about it. Okay, so the first question is to run a linear regression to try to predict the number of days of mental health. What is this? Days of poor mental health in the past 30 days. So we're trying to predict days of poor mental health using income. And we want an indicator, so yes or no, whether the individual has an income less than 10,000. So I've given a bit of code here in the notebook. So this just loads the data set, and then here I've given a little bit of code for creating predictor variables. So we're going to spend a few minutes. I want you to start to get familiar with this data set and then build a statistical model to try to predict the mental health, poor mental health days using whether the individual has an income less than 10,000. All right, any questions about this? We're going to spend a few minutes doing this. So tell your neighbor whether you like cold weather and whether you feel ready for the mini exam, and then get started with this first question. So the first step, I've given you the code to create the indicator variable under 10K, which just uses the income variable. And then you're going to build a statistical model right after that. All right. Get after it. We have a couple of minutes here. Yeah.
Yeah, so it's, this will record.
Okay, it's at 0. What happens if you
I know, I have that one.
So this just gives us just like typically each possible. So okay, what is this reports true or false, and these returns to you. So that's what that. I don't think it's really. Okay.
What?
That's right. Yeah, so we 0 or 1.
Oh my god, one you right.
Don't, because there's about 240. Because right, this is just one here. Yeah, so if it's less than the days of poor mental health. Okay, that does make sense. Because the rate of interest is assuming that it's not less, then it would be equal to a greater than $10,000. And it would be about so days of poor mental health increases if you go over and it is less than. It would be this plus that.
All right. Anyone have a number for me? Anyone have a number? So maybe let's start at the top of this question. The first thing we need to do is, like, we have income 2, which tells us, which income group the individual falls into. But what we want is a way of organizing that in a yes or no context. So, like, are they below $10,000 of income? And so what I've done here, you haven't seen this kind of code before, so I'm giving this to you for free. It's included in your participation in the class. This is just a way of constructing a binary categorical variable from a categorical variable like we have. So with this thing, let me just talk you through this for a second. If I just plot the, if I just print out the variable itself, we see all these different codes. And what we want is we want it to be true if it's below 10,000, and we want it to be false if it's above 10,000. So all I'm going to do is say, I want only the codes that are equal to 1. So this is a logical test. I'm just going to test whether it's equal to 1 or not. And this just returns a list of true and false. So we have a list of true and false, but that's not going to be good for our predictor variable. We want this to be either 0 or 1. So what I'm going to do is turn true and false into 0 or 1 by using as type int. So this turns anything into an integer, including this true and false kind of variable. So this just turns all the trues into 1 and all the falses into 0, which is exactly what we want. So that's what this is, under 10K. And what we want to do is build a statistical model that looks something like this. So this is just reg plot. I have the x variable being the binary indicator variable, and then the y variable being the mental health. This isn't a very good figure. It's hard to see the distribution of the data. So I wouldn't use this as a way of visualizing the data. It's hard to see that there's a bunch of data stacked down here. But this at least gives us a place to start. Someone want to tell me what you ran your code? Like, what was your model? What's our x variable? How many of you wrote down an x variable? Okay, a few. The rest of you did not? Did you feel lost on this question? Yes. Love the honesty. That's what I look for in these kinds of questions. Let's just walk through this together then. So someone who did write this down, what did you write? Okay, so our x variable here is going to be under 10K. So we want something that looks like y is equal to mx plus b. In this case, our x variable is under 10K, so our m times under 10K plus our intercept term. And someone else, Savi gave us the x variable, someone give us the y variable. Yeah, Hannah. Mental health. So the variable we actually want is this one. Unfortunately, in the data set, it's I can never remember how that's spelled. Mental. Okay, so this is our little model. And then we want to set this up as a regression. Unfortunately, Gemini knows how to do these things. It knows we like to use SMF. So I'm just going to tab this through. It doesn't finish it for some reason. But this is smf.ols, and then this is our formula, under 10K. And then we're going to do fit, and then model summary. Oh, let's see, data is equal to data, and we run this. I like tables. Oops, tables 1. I think this looks a little easier to read. Looks something like this. Okay. So the only difference between what we're doing here and what we more familiar, that's not a complete sentence. What we are more familiar with regressions, with a horizontal axis representing a continuous numerical variable. The only difference here is that the x variable is not continuous. It's just a binary predictor variable. All right. So I want you to turn to someone next to you and try to interpret what this is doing. A question like this will be on the mini exam. So this kind of thing where you read a regression table and then try to interpret what's going on. That's a very important skill. In fact, when we surveyed the department for what faculty wished for students coming out of this class, this is one of the big things. Can you interpret the results of a statistical model? So we'll take like 2 minutes here, try to interpret what this is telling us, and then we'll do it together.
days, and then say position is an increase of 4.8. Maybe somebody's. Well, what I always do to make sure it's very, the best thing is to look at this verbatim, but say, when income is greater than or equal to 10K, the number of days of poor mental health over the past 30 days is, and then you do that number. Slope.
Okay, someone want to interpret what your group was doing? Like, how do we read this table? We have a question which is like, if your lower income, is mental health worse for you? Yeah, Luke.
So when income is greater than or equal to 10K, the number of days of poor mental health in the past 30 days would be equal to your intercept term.
Okay.
And
So let me just pause this. What Luke is saying is, because we're coding everyone else as 0. So if your income is above 10K, you get put in this group, the 0 group. And our intercept term is equal to the average of that group. So it's the model at 0. So the number of poor mental health days for people above 10,000 in this sample is just over 3 on average. Yeah, great.
And when income is less than $10,000, the number of days of poor mental health in the past 30 days increases by 4.841 days from the number of days when it is greater than or equal to.
Yeah. So
That's a bit of a mouthful.
it is a bit of a mouthful. Maybe I'll take a shot at saying this a little more simply. But that is a correct interpretation. Let me reframe that. If you make less than $10,000 per year, you have, on average, close to 5 more poor mental health days than those who don't make less than 10K. You make less than 10K, on average, you have 5 extra poor mental health days than everyone else. That's a lot. Okay, so turn to your neighbor, tell them how confident you are in these results. Try to describe what this p-value is telling us very precisely. I gave a lot of feedback on the homework on interpreting p-values. This is a pretty important thing here. There are a lot of misconceptions about what a p-value does. So try to say this in a way that's consistent with the models we've been talking about. How do we interpret this p-value? And what does that mean for our findings? This is another excellent mini-exam question.
I feel like this is too simplistic to consider the fact that the values are 0 for the associated with intercept and the slope that's telling you that the intercept and slope are significant.
But there's no difference.
So yes, so that's, you can assert that because it's finding category, you're interpreting that as the increase from when it isn't.
All right. Someone want to interpret what this number means? 0.000. Yeah. Yeah, so this is really close. I would say that's the right interpretation for this p-value. I would say the under the null hypothesis of no difference between groups, the probability of seeing a slope as extreme as what we do is 0. It's very unlikely we see this if there's no slope. This p-value is associated with the intercept term. That's a great interpretation of the second one. Someone want to interpret this first one? I'm not giving out any lecture points because that was close. Darren.
Assuming that the sample is centered at 0, then the chance of observing this sort of these stats, like where it's centered at 3.8, and with a standard deviation or standard error of 0.016, there's a 0% chance with a t-value of 200.921.
Yeah. Yeah. So this is essentially telling us it's very unlikely that those in the higher income group have no poor mental health days. So it's saying we're very confident the number of poor mental health days is not 0. So this is a claim about the intercept, which is generally not the one that we care most about. Most of our questions when we run these kinds of models, I'm going to show you an exception today. Most of the questions we have depend on the coefficient for the slope term. So this is our m. Yeah, but this is exactly how we would interpret the p-value on the intercept term. It's like we're testing whether it's different from 0. 0 is our default null with all of these. Okay, how are y'all feeling about these questions? Yeah, Jason. Yeah, so the coefficient is this number here is the value of the m. So it's like the beta 1 parameter. So this is our beta 1 and this is our beta 0. The beta 0 will always be encoded as the intercept term. So Python will always spit out intercept. And then it will tell you the coefficient, so the beta on the x variable that we're putting into the model. So in this case, it says under 10K, and then it gives us the coefficient. This is the beta 1 on under 10K. This will become a little more important as we get into multivariate in part 5, but at this point we just interpret intercept and slope. Yeah, good. What else? Sabi?
I have a basic question about the null hypothesis for this one.
Yeah.
So you mentioned that the null hypothesis is that there is no relationship between mental health days and income.
Yeah.
So for all relation between two variables, for example, moving a project,
Yeah.
will we always consider the null hypothesis to be no relation at all?
That's right. Very good question. So Sabi's question is, here we're assuming that the null hypothesis is no slope. So beta 1 is equal to 0. That's the default null whenever we run these models. You can go through and specify something different. It takes a little bit more work, but in general, what the model takes as the null hypothesis is that the coefficient is 0. You can also see that with the intercept. So it assumes your null hypothesis is that the intercept is 0, which isn't really often the main question for us. But generally when we run these models, it assumes the slope is 0, the null hypothesis on the slope is 0, because we typically try to check for whether there is a relationship or not. So our null is that there is no slope. Luke?
So I understand that given that the p-values are 0, that's telling us that the intercept and slope are significant.
Yeah.
What else, like in our interpretation of the p-value, do we need to say again for either an intercept or slope? I know there are like a few answers bounced around, but just to know like
Yes.
concisely what to say.
It's the probability of seeing something as extreme as this slope or this intercept if the parameter was 0. So for the first one, it's what's the probability of seeing something as extreme as this intercept if there were no mental health, bad mental health days for people with higher incomes. And then for this one, this is a question about the relationship, the slope. Here we're saying, what's the probability of seeing a slope this steep if there truly was no increase in mental health days, bad mental health days for people with lower incomes? Yeah. Sabi, you had a question?
Yeah, I had a follow-up question from that previous one.
Yeah.
So you mentioned about coefficient being 0 for the I just want to confirm that means that the change in x will not affect any change in y.
That's right. So as we move up in the x variable, there's no increase on the vertical axis, which means there's no slope to that line. Yeah, what else? These are good questions. Keep them coming. Darren.
For the graph above, for sort of like a high level for test or for many exam purposes and for project purposes, what do you
Yeah.
think these like things we need to know most or like take these? Like if we like construct this on our own.
Yeah. So, like, how would we visualize the model? Is that your question?
So that and interpretations and takeaways from interpretations.
Yeah. Yep. So, I mean, for me, the big takeaway here is lower income people tend to have worse mental health days. That's what this model is telling us. I wouldn't really interpret the beta 0. I don't think that's generally important in this question. But here, we're just concluding, like, it's very unlikely that they don't have worse mental health.
I think like for the graph above with the two separated by tables one.
Yeah.
Like as a high level, what do we need to take away from that? Like from the slope, do we have to specifically make like any references in our like project to like differing the slope or?
So beyond just plotting this, I think this is a pretty good figure. Like, what I would do to improve it, I'm not sure if this is your question exactly. It's hard to see the distribution on the vertical axis of the two groups. So I would maybe try to summarize the distribution of mental health within each of the two groups. I don't know, does that answer your question? I think I'm missing what your main question is.
I think so. I was just sort of asking for like a high level of like how would we approach this when making this on our own, like for an exam. And then like
Yeah. Okay. Yeah. So particularly for your final project, I probably wouldn't ask you to like construct this on a mini exam, but definitely for your final project, I would set up the question, look at the data. How would you answer your question with the data? Build the model, and then along the way, I would try to visualize what that model looks like, and then in this case, because it's a binary predictor variable, I would use a scatter plot with the two groups. You could also do this with a bar chart. I'm sorry, with a box plot, which would give you a little bit better visualization like I do in the slides. But this is a quick and easy way to do it. And then try to visualize the model. And then once you have all of that set up, then you can interpret what's going on with the model more directly. So what do these numbers tell us? Yeah. So that's my high level. Does that work? Okay. Good questions. For the sake of time, do you want to do the second part of this question? It's very similar, just with a different number. Or do you want to talk about time series? I want to give you some time at the end of class to chat to each other about your final projects. So I just want to, can we whip through time series? This is like the least important statistical model we're going to build. But I just want to show you a couple of things. I've posted the exercise. I don't think we're going to have a ton of time to do it. But I just want to talk at you, about the problems of time series. You're strongly discouraged. You can use time series on your final project, but keep all of these things in mind if you choose to do it. So the main question with data organized through time is essentially like, is there a relationship between does something change through time? Relationships like this. So here I have a general y variable. We're going to talk about GDP in a second and unemployment. But this is, a y variable, time in days or years or milliseconds or whatever it is on the horizontal axis. And then you can see we have data that's connected through time. This is the main idea with time series. We talked about this in part 1. And we also talked about regression assumptions, or OLS, GLM assumptions, in part 4.2. The special property of time series is that the data is dependent on each other. So yesterday impacts today for any number of reasons. Like the weather is similar today to what it was yesterday. Very cold and a little bit snowy. And this special property, like the nice characteristic, or the unusual characteristic about time series, is that we have this dependence. And it's precisely that dependence that breaks one of the assumptions of OLS, of our general linear model. Assumption 4 of independence. Each one of these data points is close to the one that came before it. That's the property that makes time series stand out, but it also means it's going to give us a lot of trouble when it comes to building statistical models. This trouble is what we call autocorrelation. And we can generally check if past observations are related to future ones. So this is the figure I want you to look at. We call this a couple of things. You can call this a lag plot. So on the horizontal axis, I have yt minus 1. So this is the t variable from the previous period. And then on the vertical axis, I have the current value. So this is one value plotted against the value that came before it. So the current value is on the vertical axis, and then the one that came before it is on the horizontal axis. And just as you would expect, typically whenever we deal with anything sequenced in time, last period is closely related to this period. You can see this because if we draw a 45-degree line through the data, you can see that last period, so if you're at -2, you're going to be very close to -2 in the current period. This is a problem. If we just build a statistical model with a line that runs through the data like this, you can see that we're going to make systematic errors. To highlight this, what I'm going to do is show where the errors are showing up. So here you can see we make systematic errors in the same place over and over again. If you have a data point that's above the model, the next data point will be very likely to be above the model too. So we have this problem of correlated errors. And you can just visually see this with all of these errors being in the same direction in the same place. This is a problem because there's extra information in our model that our model does not capture. Extra information in the data that's not captured by our model. We know something extra about what happens in the next period that our model is not capturing. And that is going to be very similar. So we have a couple of things we can do here. this is the kind of model I will not accept on a final project. If you try to predict something like GDP using time, people do it. In past semesters, when we've taught this at a lower level, people have run this regression. I'm not accepting this anymore. You can't predict a y variable using time. So this is just the levels regression. So I'm trying to predict something like GDP using time. And then we just build a model like this. This is the residual plot, and you can see the clear problems here. There's like an upward slope to this thing, or something. We also have a residual lag plot, which is we take all the residuals, we plot last period's residual against this period's residual, and we get a correlation between the residuals. That is not a good thing. There's extra information that our model is not capturing. The errors are going to be correlated. So this is not a great model. In the exercise 4.4, I have some code to run this. This is slightly different. Here we're trying to predict GDP using unemployment. These are two variables, and we're trying to find a relationship between them, but they're both highly correlated with each other. So the first way of getting around these kinds of problems is to use what we call first differences. This will get you like 90% of the way there. If you do want to use time series in your final project, I strongly discourage it, but you at least have to do something like this. So all we're going to do, if you remember back to your calculations of elasticity in your intro classes, this is part of how we calculate elasticities. I'm just using like a delta, the difference between two values. So we have the value at time t and the value at time t minus 1. So this period and then last period. And then all we're going to do, instead of looking at the actual values, the levels, we're going to look at how this value has changed between these two times. So I just want to plot you a picture here. This first one is just, I've constructed some fake data. Y-axis is the value. And then on the horizontal axis, I have time. And in reality, there is no relationship through time. The truth is that there is no relationship. But this doesn't quite look right. This looks like maybe there is some relationship at certain points. But when we take a first difference, you can see we have all this random noise centered around a horizontal flat line, which gives us a slightly better picture at the truth under the scenes. And in general, when we're dealing with relationships with a trend, we can also identify underlying trends through data using this first differences model. So if there was a trend, we could still see it with a first differences model. We're blazing through these slides. I was going to ask you what you would expect here. It looks like this. It's going to look like noise, like a bunch of variation with a beta 0 that's different from 0. So there is some intercept term. This is that one exception where here we actually do care about the intercept term. The intercept term tells us something about the average trend. So how, on average, is the y value changing between each period? And the reason we're getting this is because the first differences is really just looking at, so the value on the vertical axis is how much things are changing between any two periods, which tells you, on average, how things are changing with the beta 0. Okay, any questions? So when we plot the residuals of that model, we get something that looks a little bit better. So this is the residual plot. So this is the vertical axis with all residual plots is just going to be the residual. I'm plotting this against time, but you could also plot it against the predicted value. Either way is fine. And then here I'm plotting the residual lag plot. So this is lag in the last period against the lag in the current period. I'm sorry, residual in the last period against the residual in the current period. And here, there's much less correlation. In general, you're going to see a lot less correlation when you use a first differences model. But you can also see that it doesn't fully eliminate the problem of autocorrelation. Autocorrelation, we still have some value here. They're related to each other, even if it is negative. Any questions here? So for those of you who are interested in doing time series, even though I strongly discourage it, it is allowed. Like, we cover it in class, but it's just a little bit harder. This is just some code to construct first differences. So this is just a diff operator, which gives you GDP diff. So how does GDP change through time? And then you can do the same thing for unemployment. Okay, and then a second thing we might do is find, well, I guess. So the next thing we could do is use first differences both on the x variable and the y variable. I think my code actually runs first differences on both x and y. But if we have some y value that we want to use as a predictor instead of time, we can perform first differences there too. So this is delta x as our predictor variable, and then delta y as our outcome variable. And this would tell us whether there's a relationship between increasing unemployment, for example, and increasing GDP. We generally expect a negative relationship there. It's a very similar idea here. So beta 0 would capture the trend in y. So if there's a baseline increase in GDP, you'd see that in the beta 0. And then beta 1 would capture whether there's a relationship between the two variables. So do we see increasing GDP when we see increasing unemployment? That would be beta 1. Okay, and I have some nice code here for you there too. I think this is actually exactly the same code as what I wrote for model 2, unfortunately. But this would give you the double first differences. And this is a nice model. But this is not a perfect model. You're still exposed to the problem of autocorrelation. So if you do a time series model, you need to report your autocorrelation. The last one, how many of you love macroeconomics? So like this looks familiar? There's a reason we talk about growth rates and not just growth. Sometimes we have things that grow exponentially. So when you have, GDP is a classic example here. If an economy is growing at 2% every year, GDP, 2% of yesterday compounds. We get 2% higher next year. But then the following year, it's 2% of the 2% higher from the previous year. So you have like 2% on top of 2%. This generally looks like this, where we have this exponential relationship. They look like they move slowly, and then they start moving faster. So the curve starts steepening. In this case, if we just plot the first differences, so we built this model of first differences to try to understand growth or how things change. But in this case, with exponential relationships where the growth rate depends on the values from the previous period, we actually start to see something that looks like this. So the variability later is larger than the variability early. We can easily deal with this problem by transforming the variable from a difference into a growth rate. So we can actually construct this gy, the growth rate of the y variable. And it's going to be stationary, what we call stationary, around the true growth rate, which looks something like this. So this is percent change in y. this is the change in y, and this is y. So these are three different ways of expressing the same data. And this last one is what's most amenable to a general linear model. This one has equal variation through time and is centered on the true growth rate. Okay. Like this picture? No? That is incorrect. This is a great picture. Two transformations of the same data. I spent a whole 10 minutes putting this together. All right. When we build these kinds of models, I have an example in the exercise here, but you can predict the growth rate of unemployment or of GDP using the growth rate of unemployment. This in some cases that's nice. In some cases it's not the right model. So you can make up your mind about that here. But just some code. So we can get the percent change. Isn't that amazing? You can just get the percent change with a little operator on the end. Okay, so this is time series. These are the core problems with time series. I hope I've effectively communicated to you the problems with time series, just scratching the surface. You can take entire classes of time series econometrics. Not recommended. I'm not discouraging you from doing that. It's just, it's challenging. In this class, we're really only scratching the surface on these kinds of models. If you want to do time series, we can chat about it. Any questions here? No time series homework. Homework 4.3 is posted. We've already started it. You have 90% of the tools to finish it already completed. We have 15 minutes left in class, I believe. This is a good chance to sit down and talk to your group mates about the next step in the final project, which will be a separate homework. I also want to talk to as many of you as possible over the next couple of weeks about your final projects, whether that's in my office hours or after class. We're going to spend more time after class chatting about these things. So I'd love to sit down and talk to you now or later. So yeah, it'll take a few minutes.
Maybe theoretical, not like
Yeah, I'll just reach out.
yeah.
it's like so how many speeches?
No, that's okay. You just owe us an extra 100. So you can have in that
It would be a schedule.
Oh, well, I want to pay you some votes.
So the main problem with this part is that I'm going to get a lot of data. 15 is so exactly. So if you were to get like
There is no fine, just a strength get rid of the players. The commissioner said the Dodgers win the World Series they introduced more probably just but there's I don't really know what
it's interesting. The reason I discourage it is in general.
Yeah, we're
So yeah, think about the sampling okay, yeah. There's ways of changing this. Not necessarily easier but yeah, I'd like to set up here. I just want to the way you're looking at
I'm just going to ask him to make sure that I don't keep this straight.
So you can see like Dodgers is 200.
Because I remember him saying between 2000 and 2024.
That's 8 times.
And if it would ever would, I don't know. I don't know what it's going to be. Oh, I guess it's I have no idea where she's going to have if anything, I'll just put something in the chat. I'll text him if he doesn't show up next class. I'll be like, hey, we gotta find something.
Because I'm sure there's something more like nationally, but I
Yeah.
we were like thinking like maybe it would be like better to do like in Pittsburgh just to kind
It
of.
would be more interesting for sure.
Yeah, because I was thinking like if anything we could like try to get like student survey, but like if we could like find like a data place somewhere, I feel like that would also be easier. I don't know.
There's a website that may have that kind of thing for Pittsburgh. It's like a. Let me just.
Or do you know if like Pitt would keep track of like that kind of thing? Or
It definitely
would
could
I
be.
have to, like, I probably have to ask like the site department or something. I don't know.
Yeah, you could do. I would start with the Google search.
Okay.
Sometimes these kinds of surveys are published on a website. If that doesn't turn up anything obvious, send me an email. There is a website, and I'm sorry, I'm just having taught a class,
No,
my
you're good.
recall is a little bit low.
Yeah.
It's like a data archive at Pitt. I think the probability of them having what you're looking for is kind of low.
Okay.
But you can send me an email and I'll try to find it for
Yeah,
you.
you're good.
Okay.
You're good. I'll take this.
And yeah, I mean, talking to like the psych department could work. I'm not sure who
Okay.
you would talk to.
Okay.
But that's a very interesting question. Like, if you can find that data, that would definitely be interesting.
Okay. All right. All right. I'll
Remind me
try
your name?
I'm Katie.
Katie. Okay.
Yeah. I'll try looking, but thank you. I
Yeah.
appreciate it.
What's his for this Friday second topic question? Straight figure and statistical model. Does that imply all the data has to be straight by then and summarized, or just like a theoretical figure model based on the topic?
So in place of the figure, you can say something like, if you're still collecting the data,
And is the fine like
so
I'm more concerned about the model, I guess, because I feel like you have to have the data to see how you want to fit.
yeah, that's generally so. I mean, I haven't posted the questions yet,
Sure.
but it's going to be because not everyone is the data. Yeah, just like.
And I'll get it collected. It's just, I've been so busy. But I could probably do it over the weekend. But I was just making sure to see, like, because we know what our topic in question is, and sort of how we visualize it, but we don't know, like, what the output exactly is going to look like. So, okay.
And you don't have to. The expectation is not to have.
Okay. Perfect. Thank you.
That's a good start. I think that's kind of
That was just start thinking about these things.
Okay, all right.
It doesn't have to be complete.
Yeah, I think our big focus right now, because we have the data that you referred us to, or well, not in our possession, but are able to locate it, the MIT Affection Lab. It's just trying every way possible not to make it into a time series format. Because it's like,
if it ends up with a time series, these are the best tools, and I think if anyone in the class here well prepared for this.
if it goes south, don't tell my time series professor.
Yeah, it will not. I mean, the thing is, if it goes south, you say this went south, and here's how.
Yeah.
And that's credible research.
Oh, and I have to do Python and not our studio, right?
You can use our studio if you want.
As supplemental.
I
guess because we're showing slides, we're not showing like the code.
Yeah.
Because I was
You will send me your code, but
Okay,
it
yeah.
can be an R.
I could do like the stuff if